Welcome back, student. Now this is the fourth problem here, reciprocating air compressor. This is the fourth problem actually we're done. That the numerical is that it's a basically single stage double acting air compressor, a single stage double acting air compressor which delivers 5 meter cube of free air per minute at atmospheric pressure is given as 1 atmospheric pressure and 20 degrees Celsius condition to 7.5 bar. So basically double acting compressor. Initial pressure is given at atmospheric, that is 1 atmosphere, to final pressure 7.5 bar with following data that cylinder piston, that is revolution piston, that is n rpm, n is equal to 300 rpm. Mechanical efficiency is given as 0.9. Now the pressure losses, because when the air is flow through the intake valves, there are some losses of the pressure actually in basically 0.04 bar, and the temperature rise because of the friction between the air and the pipe. So there are some temperature rise actually during this suction stroke, that is 12 degrees Celsius. Okay, and the value is given as clearance volume is equal to 5% of stroke volume. Okay, and the value of n means the polytropic process. The value of actually the compression process takes place in polytropic nature. A value of n is equal here 1.3. That means PV to the power 1.3 is equal to constant, and the length or stroke is equal to 1.3 times of bore. Okay, now you have to calculate the power required to the shaft, second volumetric efficiency, a third cylindrical diameter. Okay, now value is given as VA, basically free air delivery, that is equal to 5 meter cube per minute here. Pressure, atmospheric pressure is given as 1.013 pressure bar actually. Atmospheric temperature is 293 Kelvin. P2 actually final delivery pressure, that is equal to 7.5 bar, and N actually speed, that is 300 rpm. Mechanical efficiency 0.9. Pressure loss, that is 0.05 bar. Temperature rise 12 degrees centigrade, and clearance volume, that is 0.05 times of Vs, and N is equal to 1.3, and stroke, that is given as 1.3 times of bore. Okay, now just these are the values are given actually. These are the values are given in the numerical. If you go through it, you can write down. Next, now the next part is that so V1 actually, so this is the VA actually, it can VA, but you have to, what is VA? So V1 is equal to volume of free air at suction condition. So V1 is your volume of free air at suction condition. That is not given in numerical, but what is given here, that the pressure loss when the air passes through the intake valves actually. So actual pressure is P1 will be PA minus amount of losses, that actual pressure, that P1 actually 1.013, as we know that these are the atmospheric pressure, and value are given also given here. So minus of 0.04 bar. So P1 will be 0.973 bar. You just convert into Newton per millimeter square. Okay. Now, so obviously if it is a pressure loss are there, so temperature can be increased because of the friction between the air, or viscosity between the air and the pipe. Okay, so temperature, actual effective temperature, that's the initial temperature, that is T1, that equal to ambient temperature or atmospheric temperature plus temperature rise, that 12 degrees Celsius. So actual temperature initial condition will be 3.05 Kelvin. Now, as you know, the air actually follows the ideal gas equation. So we know actually the ideal gas equation, what is that is equal to, if we apply on that, so P1 PA VA divided by TA equal to P1 V1 by T1. So from that equation you can calculate the value of V1. Okay, now PA VA value of PA, that is basically atmospheric pressure 1.013 Newton per meter square. VA value of actually free air delivery, that can basically 5 here, and okay, so that is basically T1, that is initial condition of temperature, that is 305 Kelvin. P1 value is 0.973 is given here, and TA atmosphere, that is 293 Kelvin. So V1 will be 5.42 meter cube per minute. Okay, so V1 is actually volume of air, that is intake, that intake condition of the volume of the air, that is basically 5.42. Okay, now in the first calculation is that what is the what is the actually power input to the shaft. What is the power input to the shaft? Now, power input to the shaft, that is, we know that what is the indicated work done actually. Indicated work done is, we know that the formula or the expressions, if the process follows the polytropic process, so the expression is basically n by n minus 1 into P1 V1 into P2 by P1 to the power n minus 1 by n minus 1. Now value of n is given 1.3 and P1 value is actually 0.973 because of pressure loss, because 0.12 bar is basically pressure loss during the flow of air into the pipe. So actual effective pressure P1 is 0.973 into 10 to the power 5, just convert into here, into V1 5.42, write down this value here. Now P2 by P1, so P2 is the final delivery pressure, that is 755 bar, it is given in the numerical and it also given. Now n value of n is given in the numerical, so 1 n minus 1, that's why 0.3 divided by 1.3 minus 1, so that will be 1370 into 10 to the power 3 joule per minute. You just convert into kilojoule per minute, so that will be 1370 kilojoule per minute. Okay, now this is the indicated work done. As you know, this is the, if it is a indicated work done, so indicated power will be 1370 divided by 60, you just convert into kilowatt. Okay, so that will be 22.8 kilowatt. So this is the indicated work done. Now the value of mechanical efficiency of the compressor, that is basically given as, that is basically I think 0.9 it is given. Okay, now as you know that mechanical efficiency is basically the ratio between indicated power divided by power input to the shaft. Okay, power input to the shaft. Now here indicated power is 22.8 kilowatt. Actually this power actually used for running the compressor, and actual power what is given to the compressor, that is basically power input to the shaft. So this is the ratio between two. Now as you know that efficiency basically output by input, so input will be very much higher compared to the output, so obviously power input to the shaft actually very much high compared to the indicated power, because of there are some losses, there are some as like friction loss, pressure loss, like this type of losses, bearing loss, some any other types of machine loss will be there, obviously in terms of multiple losses are there. So there are some losses, so that it basically adjust. Okay, so basically the mechanical efficiency is the ratio between indicated power divided by power input to the shaft. Now value of mechanical efficiency is given that in the numerical, that is 0.9. Now you know that the value of mechanical efficiency and the indicated power, but you have to calculate the power input to the shaft. So power input to the shaft is equal to indicated power divided by mechanical efficiency. Now indicated power is equal to 22 kilowatt, so write down this value 22 kilowatt divided by mechanical efficiency 0.9, so that will be 25.3 kilowatt. In between two these values, the power input to the shaft, that is basically high quantity and that is basically less quantity, because of there are some losses, there are some actually friction loss, pressure loss, there are so many other losses up there, so that's why that adjust here. Okay, now in the second part you have to calculate the volumetric efficiency. In the previous lecture video we already know that the clearance ratio, that is basically C is indicated as clearance ratio. Now clearance ratio is the ratio that is the between clearance volume, that is basically VC is your clearance volume divided by swept volume. Now clearance volume in the numerical, the value of VC is basically given as 0.05 times of VS and divided by VS, so VS will be cancelled out, so VC or C actually value is 0.05, so the clearance ratio is 0.05, and you know that the volumetric efficiency is equal to 1 plus C minus C into P2 by P1 to the power 1 by N. So value of C is 0.05 here, just put down these values, write down these values here, and 0.05, 0.05, and P2, you know the value of P2 in the numerical, and P1, just write down these equations, you can get the values 0.809 or 81%. Okay, and the last part of the numerical, and that is basically what is the diameter or what is the bore of the cylinder. Now as you know that the swept volume, piston cylinder volume, sweep volume is basically Vs, or piston displacement volume. You can calculate by, as it is in cylindrical shape, so pi by 4 into d square L. So in the numerical, the value of so pi by 4 into d square, so L is equal to 1.3d. It is given in numerical, just follow up. So L is equal to 1.3d. So write down this here. So actual sweep volume will be, so the next page, so Vs is equal to 1.02 d cube. Okay, now we know that this compressor basically double acting, so number of working stroke per minute will be 2n. Okay, 2n. As it is this double acting, which is single acting, that is n. If it is a double acting, that will 2n. Double acting, so number of working stroke per minute will be 600. Okay, now sweep volume per minute, so these are sweep volume per cycle actually, and sweep volume per minute will be 1.02 d cube into 600, so that will be 612.6 d cube. Okay, now as you know the volumetric efficiency, now you have to calculate the diameter. Okay, you have to calculate the diameter of the cylinder, or you can say the bore of the cylinder. As you know that the volumetric efficiency is basically the ratio between the ratio of the actual volume of gas taken into the cylinder during suction stroke, that is basically V1, to the piston displacement volume, that is nothing but sweep volume. So V1 by Vs. So V1 value is already we have calculated in the previous page, actually that is 5.42 divided by Vs sweep volume, that is basically 612.6 d cube. So 612.6 d cube. Okay, as you know that NV means volumetric efficiency equal to this one. So we know that volumetric efficiency in the last part of the numerical, that is 0.81, we already know that value. So from that expression you can get the value of D, or diameter of the cylinder, or you can say the bore of the cylinder. Okay, so that will be D is equal to 220 millimeter. You just convert it to meter to millimeter here. Okay, thank you very much for listening and watching me, and goodbye.